So let's look at a basic example of a ring rolling simulation in QForm, from preparing the geometry for simulation all the way through viewing the simulation results. The QForm ring rolling simulations are based on SMS Group and SimpleCamp rolling mills. 3D geometry models for ring rolling simulation can be prepared in any CAD system and imported to QShape to generate the finite element mesh. We'll show some steps of the geometry preparation in ANSYS SpaceClaim CAD system. It's generally easier to use your CAD program to draw or combine 3D models of tools in one file and position the objects relative to one another. For demonstration in this example, we have 3D models of each tool in different files, so we'll bring them into a single workspace. We've also modeled the workpiece for this example, but you can also use a workpiece that has been generated in a forging simulation as the starting shape for a rolling simulation. As we see, all the objects keep their original workspace origin, so we'll need to position them together based on the design of the rolling machine. It's a good idea to rename objects according to their functions so that we can easily keep track of multiple objects. Let's look at the workpiece as the base object to be used for the positioning of all the tools. So we create an XZ plane to allow for easy positioning and rotation of objects in a cross-section. We'll have to make sure that all the objects have axis of rotation at y equals 0. The x and z coordinates of each object can be anywhere you like. Move the main roll in the minus x direction to place it close to the workpiece but not intersecting it. Then we position the guide roll to its location and mirror it about the vertical plane to create the second guide roll. The mandrel is okay the way it is, so we don't have to change it, since it will be placed in contact with the workpiece in QForm when the simulation starts. The positioning of the axial rolls is interesting in this example because the technology requires them to be placed so that the contact areas are horizontal. This means that the rotational axis will be at some angle determined by the angle of the cone shape. So there are two ways to do this. The first one is to rotate the roll by the cone angle and move it up to contact the workpiece. Now this method is simple, but it's not accurate. So we actually recommend using a special tangent function to locate the cone. Then we mirror position the axial roll to create the second one. Now in some rolling machines the axial rolls may not be symmetrical, so in that case you'd have to position it according to the machine requirements. At this point, the 3D geometry is ready to be imported into QShape to generate the finite element mesh for the ring rolling simulation. We have a SpaceClaim add-on called QForm Direct that makes this very easy. So we just click the QForm Direct button, and now we're ready to move to QShape with our geometry models. We have another video that's a more detailed QShape tutorial. So here, we're just going to quickly generate the mesh without explaining how to detect and fix the defects. After you are sure the geometry has no defects, click Mesh Generation for each shell model, and you can see that the shells are changed into solids. After all the models have been meshed and are solid, we need to convert them into the appropriate tools and a workpiece so that the program knows what the solid objects are. Select the workpiece solid model and click Convert, and then choose Workpiece 1. Select the other solid models and convert them to the appropriate ring rolling tools. After all the objects have names, save file, save as, and specify a name and path for the completed geometry being saved. Now open the QForm program. And at this point we'll need to specify all of the initial data for the ring rolling simulation. Because of the many revolutions required for the ring rolling process, an accurate simulation of the ring rolling requires a huge number of records. For ring rolling simulations, QForm uses a dual mesh method with two overlapping meshes. There's a geometry mesh that contains the information about the thermomechanical fields and maintains the shape of the body, and a separate computational mesh that's used for calculating the plastic flow equations. This dual mesh method provides very high accuracy while allowing quicker simulations. So to start a new simulation, click Create New Operation. Name the operation and select the process type, ring rolling. You'll see an additional tab appear called Process Parameters that includes all of the special ring rolling data needed. So we click forward to the Geometry tab where we load all the geometry models needed for simulation. So click Load from File and select the Q-shape SHL file that we have just saved. We need to specify the axis of rotation for each tool, so click Axis Command. And we don't need to set rotation axis for the workpiece, so choose the main roll and then enable Axis 1. An axis may be specified by either 2 points or by 1 point and a direction. When setting the direction of an axis, it's a good idea to enter a big value so that you can see it easily in the graphic window. Specify axis for all the tools in the same way. And if you don't know the coordinates of the axis, you'll have to go back to your CAD model and find the center through your CAD software. If you set an axis by specifying 2 points on the object, you may not see the object because it might be entirely inside the object, like in the axial rolls in our example. The guide rolls have 2 axes of rotation, so enable axis 2 for those and specify the second axis for it. Check if all the objects are placed in the XZ symmetry plane. When all the axes have been specified, click OK and then Forward. In the Workpiece Parameters tab, select the material type and the initial temperature of the workpiece. We will use the material 28Mn6 at 1250 degrees Celsius. The next step is specifying tool parameters such as lubricant, tool material, and temperature. For this ring rolling process, we will use the Siebel friction model with a 0.95 friction factor. If it's not available in your database, select unlubricated, switch to Siebel, and set 0.95 as the friction factor. Then save this new lubricant and click Assign to set it as the lubricant used for the simulation. Set H11 as the die material for the tools and set the running temperature of the tools at 300 degrees Celsius. Next, in the Process Parameters tab is where the different rolling parameters and equipment characteristics are specified. Velocity of main roll is in RPMs, or how many revolutions the roll will make in a minute. So set this parameter to 30. Finish diameter is used to define one of the simulation stop conditions. So set it to 2,200 millimeters. Leave the standard load on centering roll at 0.1 meganewtons. The kinematics of the rolls can be specified in one of 2 ways, either by specifying the ring growth speed and height to thickness table from charts, or by using radial mandrel velocity and vertical velocity of the upper axial roll. Now, which method you choose will depend on the data that you have available. In our example, we'll use the table method. So let's go ahead and specify a table by clicking the Select command next to the ring growth speed. Click Create and set the number of diameter values that you have velocity for. We'll use 4 values. Fill in the cells of the table. Save it and click Assign. Create a height to thickness chart in the same way. Set the number of thickness values to 2 and fill in the table. In this example, we don't use automatic positioning, so click forward to go to the Stop Conditions tab. Click Add Condition and then Time, and then enter 250 seconds for a stop condition. So remember that we also entered a final diameter stop condition earlier, so the simulation will stop when either 250 seconds process time has elapsed or when the finished outer ring diameter reaches 2,200 millimeters. In the Boundary Conditions tab, we don't need to change anything, so click forward and get to the Blows tab where we can specify the time of billet cooling in air before the rolling process starts. Next, in the Simulation Parameters tab, we don't need to change anything. This is where we could modify advanced default values such as mesh adaptation factor, which would affect the size of the mesh elements and the accuracy and speed of the simulation, the simulation step multiplier, which would allow us to increase the simulation speed but decrease its accuracy, and some other advanced parameters, but we don't need to change anything here. So now we have entered all the initial data, so we can start the simulation. Click Start Simulation and confirm saving the project. Now after the simulation is finished, visual results are shown in the graphics window. The rolling simulation can be played back and the various fields can be looked at. To build a diameter to time chart, click the graphs icon on the toolbar. Click Add Graph to the left and select the parameters and functions. This graph can be saved by clicking Save to File and setting the name and directory. We can save a video animation of the simulated ring rolling process too. To do this, position and rotate the simulation results as you'll want them to appear in the video. If you want, you can show a cross-section during playback and choose any workpiece or tool field, for example, plastic deformation distribution in the ring. Then, click the Image and Video Creation button. Choose Type of File, Path, Time of Animation, and enable the checkbox if you want to save a legend that'll show what the values on the field is. The video will be saved in Windows WMV Wave Movie format. Alright, thanks for watching.